Welcome to MITRE's Grand Challenge Power Hour. Here's our MITRE Vice President of Engineering and Prototyping, Doug Robbins.
Good afternoon, everyone, and thank you for joining us to kick off our 2022 MITRE Grand Challenges Power Hour series. Big data, machine learning, AI, these are hallmarks of the fourth industrial revolution, which is rapidly evolving, and so is our climate crisis. And at the intersection of these is an important topic like remote sensing, where data can provide a window into what's happening in the earth, coupled with big data analytics, and this can offer scalable solutions. So that's what we're here to talk about today, about the technology, the applications, and the implications of this very important good. But before I introduce our moderator and get going, a few housekeeping rules to think about. First, the event is public and open to the press, so please keep that in mind when commenting and posing questions in the chat for our speakers. Also, if you're interested in helping us solve this big challenge or any of the other challenges MITRE's tackling, we'd love to hear from you. We are hiring. You can reach to recruitinghelp@mitre.org for more information. And last but not least, we will have a link to more information about each of the speakers in the chat as we go along with the program. And we do want a robust conversation, so please don't hesitate to put questions you have for them in the Q&A section, and we will have time for Q&A during the panel discussion. But with that, it's my great pleasure to introduce today's moderator, Hale Miglarese. Anne is an environmental science and geospatial solutions executive with a focus on bringing new technologies to market. She presently serves as the Impact Science Executive Program Officer for Saildrone, but has a long history of this. She was the founder and CEO of Planet IQ, of Virgo Earth Data, and most recently, the Radiant Earth Foundation. She was the first chairperson of the National Geospatial Advisory Committee, and among many other honors has, in 2019, received the NOAA Vision Award for her lifetime body of work. She has three professional passions. The first, very much related to today, or all of them, embracing new technologies that enhance mankind's ability to map, quantify, and understand the Earth and society's impact on the Earth. Second is building truly all organizations that span all sectors of society to answer the questions of where and why. And last, but certainly not least, mentoring young professionals. She has a BS and MS in geography from the University of South Carolina, and it is my pleasure to welcome Anne today.
Thank you, Doug. Welcome all for what I'm sure will be an interesting and thoughtful 90 minutes of conversation. I'm honored to participate in this webinar along with three outstanding thought leaders and most importantly, doers in the Earth observation and climate change space. Joining me today will be Stuart Collis of the Bill and Melinda Gates Foundation, Dr. Stephanie Schollaert from NASA Goddard, and Dr. Stephen Hamburg from the Environmental Defense Fund. The design of our conversation is each speaker will present for 15 minutes. At the end of those three presentations, we will have a roundtable discussion and then take questions from the audience. Please use the Q&A button at the bottom of the Zoom interface to submit your questions for review. So with that, let's get started. Stuart Collis is a Senior Program Officer for Digital Agricultural Solutions at the Bill and Melinda Gates Foundation, where he focuses on digital farmer services, smart farming, and digital support systems for small-scale crop and livestock producers in low and middle-income countries. Mr. Collis has over 20 years of experience in agricultural information technology and was co-founder and CTO of Aware, where we originally met. Aware is a benefits corporation providing global ag weather content, agricultural modeling, and analytics to private and public sector partners. Previously, Stewart worked on climate-driven spatial crop simulation modeling and ag data management tools at Texas A&M University and the International Center for Research in Agroforestry. Stewart has a Master's of Engineering Science and Geomatics Engineering from the University of New South Wales in Sydney, Australia. So Stewart, thank you for joining us today. What do you have to share with us?
Thanks a lot, Anne. I really appreciate being invited to present to you today about Earth observation in agricultural development. And I'd like to start my session just with a brief video that Bill produced for Gates Notes. If we could bring that up, please, to give a quick overview and background on agriculture and small-scale producer challenges in the face of climate change.
Tragically, billions of people who are least responsible for greenhouse gas emissions will suffer the most from climate change. Imagine you're a farmer in Kenya. You work a 2-acre farm to feed your family. You produce approximately 55 times less carbon than the average American. But now suddenly you're dealing with drought or flash floods or locusts. Even if there isn't a catastrophic event, the land you rely on is producing less, and you are already on the edge of survival. Worldwide, there are 500 million smallholder farms like this. In many low-income countries, more than half the population works in agriculture. So when small farms fail, whole economies fail. And that means more poverty, hunger, and hardship. That's why it's so important that we make agriculture more resilient. We need innovations like crops that are resistant to drought, disease, pests, and weeds, digital tools that get farmers the information they need to adjust to changing conditions, financial services from insurance to credit to protect farmers from catastrophic loss. If we're serious about addressing climate change, we have to invest aggressively in 2 goals. First, advancing the technology and policies to get to net zero emissions by 2050. Second, protecting the livelihoods of families in danger of losing them to an already rapidly changing climate. That's how we avoid a climate disaster.
Thank you very much. So kicking off, if we could move to the next slide, please. I'd just like to give a little background on the Agriculture Development Program at the Gates Foundation. Of course, we're mostly focused on the second point that Bill made there at the end of the video on protecting livelihoods for small-scale producers. That means that we're working on helping farmers move from subsistence agriculture to a small commercial farming. Farmers in the commercial world are then contributors to economic growth. And we're focused on several impact goals. We're focused on agricultural productivity for small-scale producers, increasing small-scale producer household incomes, increasing equitable consumption of safe and affordable nutritious diets year-round, and increasing women's empowerment in agriculture. So these are the guidelines under which we work and we develop our investments. I'm just going to run through a few slides very quickly. Bill's already mentioned a lot of this in the video, but if we go to the next slide, as he spoke about, we're starting to see incredible amounts of climate change. And if you could click again, please. We see increasing extreme events, whether they be droughts or floods that we saw in Zimbabwe last year and droughts in Kenya the last couple of years in northern Kenya. Next slide, please. We also see more gradual changes around the amount of rainfall occurring, changing seasons maybe getting shorter, or the starting date is changing. And these are obviously having dramatic effects on smallholder farming systems that don't have tools to adapt to these types of changes. Next slide, please. As we see the environment changing, we're starting to see occurrence of pest and disease that we haven't seen before. You may have seen in the news there were some rather large locust outbreaks in the northeastern part of eastern Kenya this last year and the previous year. We also had some fall armyworm issues in East Africa. So as these types of issues increase, we've got to have systems that allow us to predict those and have more visibility to where those issues are occurring and where they're likely to occur. Next slide, please. At the same time, farmers are faced with trying to maintain soil health. The African continent especially is a very old continent with very old soils. And so keeping nutrients sustained for sustainable agricultural systems is critical to the long-term sustainability of these farming systems. So that's a difficult challenge when you've got these other issues to address. Next slide, please. And one of those issues is lack of relevant and timely information. Farmers often don't have the chance to speak with extension agents. They might see one once a year, if that, and women in particular are usually not, don't have any access at all. So obtaining relevant information that's up to date and the most recent best practices for farming is a real challenge. It's an information asymmetry that exists. And next slide, please. And then supply chain and market access is also a challenge, not just locally, but for accessing global markets and the efficiencies of those supply chains in farmers getting, small-scale producers getting appropriate pricing for their produce. And then next slide. And we've all seen the effects of COVID. I mean, we've seen that here domestically in the US with inflation affecting the economy and food prices being affected. Of course, that's exacerbated when you're talking about small-scale producers that are earning just $2 a day, where we've seen almost 20% increase in food inflation. And it's projected that there'll be an estimated 840 million people hungry in 2030, which is 210 million more than was projected in 2015. So huge challenges ahead as we face these types of shocks, whether they be climate or COVID-like shocks. Next slide, please. Now, I'm in the digital agriculture space and digital farmer services specifically. And there's a myriad of solutions out there that are trying to solve a lot of these challenges. Looking at supply chain issues and advisory and finance and so forth. Over 400 in Africa alone and many more in India. If we move to the next slide, please. And we see an impact here. We see increases in income, increases in productivity for each of these types of solutions, especially when you bundle those solutions together. So we see a multiplier effect on income and productivity increases when you say, for example, include an advisory service with a financial service, increasing the likelihood that that credit or that loan would be repaid using best practices. So they're reinforcing one another. The next slide, please. And now, just to talk a little bit about how does Earth observation and remote sensing fit into this landscape. Next slide, please. And I'll just run through a few examples of that. This is broader than digital farmer services specifically, but there's a lot of use of remote sensing for food security analytics and also for these food price indices that are being developed. A lot of governments today don't have visibility to what the total production is going to be in a country. So if we're looking at a shortfall in maize production or rice production, this of course affects exports and imports and prices. So there's a lot of efforts to try to leverage remote sensing more in a collective way, a regional way, to monitor this type of crop production and using crop analytics and satellite-derived analytics. Next slide, please. We also are using remote sensing for crop research. So we spend a lot of time and investment around upstream crop varietal development, for example. And so understanding agroecological zones and how those zones are shifting, how varietal regions are changing and growing seasons are changing is really important for us to be able to understand what types of varieties need to be in the pipeline to adapt to climate change. And so having high resolution data from products like iMerge and the GPM platform is really critical for us to be able to do that type of market analysis on those new variety developments. Next slide, please. And another click, please. And then, sorry, previous slide. The build is not working. If we look at also soil property mapping, I mean, this is, we have Sergo in the United States, but in Africa, for example, we didn't for a long time have much on soil properties. So having visibility to soil properties allows us to provide appropriate agronomy and advisory for farmers which is something we've recently produced with an investment called ISDA, where we have both 250 meter and 30 meter resolution soil property maps. Next slide, please. And then, of course, early warning systems, having visibility to seasonal changes, seasonal forecasting, climate risk analysis to allow us to assess when a food crisis might be emerging, or when we need to advise farmers to take different actions, plant earlier, consider different varieties, and so forth is critical. Next slide, please. The pest and disease I talked about already, and there's applications out there to collect data in the field and provide immediate advisory on what to do about that issue. But if you aggregate that information and extrapolate out using remote sensing, we can start to get visibility into the spatial distribution of those issues, and enables mobilization of support for small-scale producers to tackle some of these new problems that are occurring they've not maybe ever seen before. Next slide, please. And then field boundary detection is an interesting area where I think AI and ML can really play a role. You know, a lot of farmers we work with don't have land tenure. We don't actually know where they are. We might have their phone number, but we don't have a boundary within which they're operating. And so, you know, with that boundary information, we can, of course, apply satellite imagery with that geospatial area and provide, you know, things like advice on, you know, crop health and timing of certain messages that might be relevant for that farmer at that particular time. Next slide, please. And then that localized advisory, that's really going to be driven by, you know, everything I showed earlier. So having some of these satellite-derived crop health maps, you know, having these harvest yield predictions, you know, harvest timing, you know, planting timing, you know, tailored agronomy based on those soil maps I talked about. And as I mentioned, farmers often don't have access to extension agents. So getting that information very easily, very directly through a feature phone is really what we're talking about. So we're talking about very sophisticated cloud-based solutions, but then at the end of the day, when we're delivering that information, it's got to be very easy to use and very easy to access. Next slide, please. And then finally, just one of the key components here, and I think, you know, this has already been using satellite remote sensing for insurance products and finance. So insurance, people are using it for those agroecological zone mappings so that they can define the right policies that match those farmers' needs and the environment in which they're working, so that a payout kicks in at the right time, depending on the crop loss they most likely experience due to monitoring the climate there. But then also on finance, a lot of farmers, as I said, don't have land tenure. They also don't have collateral. And so looking at ways that we can develop alternative credit scoring systems that allow banks and financial institutions to have a better understanding of the types of risk that they're undertaking to provide credit to small scale producers. So having that historical information of crop health at a particular location for the last 10 years, or the weather for the last 10 or 20 years, can help inform those types of models. And next slide, please. So just I'll finish on a project that we're working on that you may be interested to have a look at. Is a project called Enabling Crop Analytics at Scale, managed by our partner Tetra Tech. And what we're looking at is, what are the challenges we see in remote sensing, specifically across all of those applications, the lack of ground truth and training data. And so a lot of groups are collecting that type of data. They maybe have some of that data, but it's not particularly accessible to others. A lot of people have small bits here and there, but we don't have a comprehensive view across a geography. And so we're looking at different data models and data sharing models to incentivize actors to share and collaborate on that type of data and information. And there may be a marketplace option. There could be some global public good components to that. We're very reliant on crop cuts at the moment. A lot of people collect that data, but we're also talking about innovations in the space. So how do we lower the cost and increase the quality and volume of ground truth and training data? And we're looking at new technologies like ground LiDAR, or LiDAR on a phone or a tablet, or just simple photographs, low-flying drones. We're providing some funds to innovate in this space to improve the quantity and quality of ground truth data, and then trying to pair that with the data sharing model. If you're interested in more, please go to the website listed here. We actually have a stakeholder database that we're collating. And so if you navigate to the stakeholder page, we'd love to get you to input your work if this is an area you're interested in. And you can reach out to the team on the website as well. And then I'll just finish with a final slide on innovation. Specifically is, this was a quote from Bill's book on the climate disaster, is thinking about innovation, not just in terms of inventing a new product or service, but how do we then scale that service? And that's a lot of what we're working on. We need that pipeline of new inventions, but we've got to really scale those out to millions of farmers. One of the problems we have is that many of the solutions out there are reaching a small number of farmers, but we've got 500 million farmers to reach, and we're facing a climate challenge here in the future, as well as food availability. So innovation is one way in which we can address those issues. And with that, I'll close. Thank you very much.
Perfect. Thank you, Stuart. Just a couple of questions. I don't worry so much about industrial agriculture. I'm sure they will adapt. They have access to finances, they have the science, they have the supply chains, though I'm sure we'll all pay more for what we eat. What I worry about is, how do we really support those 500 million small leaseholder farmers across the globe? We have much of the data, sure, we need more. We're certainly developing the algorithms and the training data sets for ML at scale across Earth observations. I was really encouraged to see that market map for Africa that you showed. As you know, I've followed this field for a while, but scaling this industry is all about that last mile, right? And what obstacles do we have to overcome to deliver the crop intelligence at that last mile, to make it actionable information for those small farmers in developing nations?
Yeah, thank you for that question. It's certainly a challenge. I mean, farmers, small scale producers in low and middle income countries absolutely need these services, and finance, insurance, subsidy programs, advisory, market linkages. And governments are really challenged to provide these services on their own. They often don't have the digital infrastructure or the digital tools to really scale these solutions. And so we see, as that landscape map showed, there's an awful lot of solutions out there, but as I just mentioned, a lot of them are really challenged to reach scale. With over 500 million farmers to reach, we've got very few of those solutions have reached more than 1 million farmers. And I think that's for multiple reasons. Agriculture is a very tough market. It's very lean, even in the United States. A lot of ag tech companies are challenged to sustain themselves. And especially in low and middle income countries, it's a riskier investment for even for impact investors. So I think the cost of these services need to be very affordable. Small scale producers only earning $2 a day, can't afford to pay much for these types of services. So how do you distribute the cost of those services across, say, financial institutions, input providers, off takers is one way. I think also there's barriers around language, literacy and digital skills, and access to handsets. One of the big costs for farmers is their mobile data plan to even access these types of information services. So I think lowering those costs is another area. And then that data infrastructure is very challenging. There's not a lot of global public goods like the soil map I showed. So how do we improve on those types of elements so that these ag tech innovations and digital solutions don't have to build the whole stack themselves? So a lot of issues, but we're working to address as many of those as we can in the development community. Okay,
great. Thank you, Stuart. Well, I'm sure we'll have many more questions for you as we come back around to the roundtable session. So next, I want to introduce Dr. Stephanie Schollaert. Stephanie is an applied science manager at NASA Goddard Space Flight Center, where she leads activities in to advance the practical applications of NASA's Data and Science, connecting researchers across the Earth Science Division with end users in developing external partnerships and fostering innovative uses of Earth observations for societal benefit. As a part of this effort, she leads a team that convenes 6 working groups with scientists and stakeholders around food security, air quality and health, climate and environmental health, disasters, mission applications, and the Chesapeake Bay. Her research focuses on the response of marine and aquatic ecosystems to physical forcing through the use of satellite data, in situ measurements, model outputs, and statistical reconstruction. Stephanie has a PhD in atmospheric and ocean sciences from the University of Maryland, a Master's of Science in Physical Oceanography from the Graduate School of Oceanography at the University of Rhode Island, and a BS in Oceanography from the U.S. Naval Academy. Stephanie, thank you for joining, and we look forward to what you have to share with us today.
Thank you, Anne, and thanks very much to Victoria and MITRE for inviting me to this really interesting discussion. So I'm going to start, my slides will come up. I'm going to start with an overview of how NASA studies Earth as a system. And if you could click on this is an animation, exactly. So this demonstrates all of the different variables. We've got about 20 satellites monitoring different geophysical variables from vegetation on land, in the ocean, soil moisture, precipitation, salinity in the ocean, temperatures, winds, and clouds, obviously. And all of these we can see through satellite looking at Earth. All of these are interrelated. So, you know, the precipitation leads to soil moisture, which leads to vegetation, and then later on that can lead to fires. And by studying Earth as a system like this, we have really gained a lot of insights into how the water cycle, the carbon cycle, and the energy cycle are interrelated. But the biggest challenge for us, for NASA, is we have this understanding globally, and we have the combination of the satellite data, and then we also have a lot of in situ data that is essential for calibrating and validating the satellite data, and then assimilating into our models where we can do predictions and projections. We have these at a global scale, and so our big challenge is how can we scale it down to deliver it locally at the resolution and scale that people need for decisions. So next, please. So this is our current fleet, and our future fleet is shown in the orange at the bottom there. So we have approximately 20 Earth observing satellite systems in partnership, many of them in partnership with other agencies and international agencies as well. So, for example, the most recent launch was Landsat 9 with our USGS partners, and that's extending the legacy of the Sustained Land Imaging Program, which has been going for over 5 decades. So that's really important as a climate data record data set. And I'll mention now that from my role as applications, what we're doing with missions in the past, because NASA is a research agency, we would launch missions, data would be collected, and then we would work with NOAA and other agencies, USDA, to figure out how to apply the data to practical decisions. But now we're thinking about this early on in the mission study and design phases. We're addressing applications. We're starting working groups with our stakeholders, and we're getting their feedback early on to consider this with the engineers in mission design process. And the hope is that we can, by doing that, we can benefit society more and have, if there's any kind of adjustments that need to be made, that could help get more value from these. Next, please. So specifically on the topic of climate change, I just want to mention a couple of different activities. I'm going to run through a lot of examples of work done by other people across the agency and across Goddard, and at the end I'll talk about my own project and research in water quality. But on the topic of climate change, we've got a number of new initiatives, including this week, our new chief scientist and senior climate advisor was announced, Dr. Kate Calvin. We're also working with other federal agencies to integrate our science and data products into a climate resilience information system. And then, you know, we've got the disasters program, and this is an example. One of the other activities NASA is doing right now is called Climate Adaptation Science Investigators Working Group, which is looking very closely at all of the NASA centers and facilities. The idea being, if we can use all of our science information and downscale it and be heard within our own agency and have our own facilities adapt and be more resilient because of that, then what we learn in working with those facilities managers, we can then scale it to the communities around the centers and then hopefully to the larger population. Because it's not an easy task to figure out how to do this and to figure out what needs to be downscaled. The project right now is specifically focused on extremes of temperature and precipitation, fires and air quality, coastal and inland flooding, and sea level rise. And this is an example from 2017 when Hurricane Harvey hit Houston. That Climate Adaptation Science Investigators Group had been meeting and advising Johnson Space Center. And because of that, the impact of all that extreme rainfall was less, and the stormwater runoff was somewhat mitigated. Next, and this, I'll mention, this activity is being led by Cynthia Rosenzweig at NASA GISS in New York, which is part of NASA Goddard. So just today, you probably heard the press release by NASA and NOAA about the 8 warmest years on record have happened in this decade. And I think 2021 in particular was the 6th warmest for air temperature. But earlier this week, there was the news put out that it was the warmest in the ocean, which is extremely concerning because the ocean has a lot of thermal inertia. And so a warming ocean, the ocean has been a big buffer against climate change, and a warming ocean is very, very serious. We don't even completely understand all the possible ramifications of warming our oceans. Okay, next, I'm going to fly through a lot of examples. The 2021 disasters season had, NASA was monitoring a lot of the different disasters, from the tornadoes in the Midwest, Hurricane Ida, and typhoons. And we provide a lot of information. We have a disasters portal to support risk reduction, response, and recovery. We're working very closely with FEMA and other agencies, and then internationally with aid organizations and others. Next. We can also see in our satellite record the cryosphere, and for example, the Arctic sea ice has been declining 13% per decade. Next, that gets released every September. Between our satellites and our in situ observations that are assimilated into our models, we can see that carbon dioxide levels are the highest they've been in 650,000 years. This is an animation you can find on our website where it shows CO2 emissions and then transport in the atmosphere. And you'll notice that most of it is in the northern hemisphere where the industrial emissions are. Next. And then we can see vegetation. So here's an example of a researcher who looks at deforestation in the Amazon. And with the Landsat record that's almost 5 decades now, we can see land use changes. So this is critical for understanding the terrestrial carbon sink. Next. And then working together with some of the commercial satellite providers, a recent study by both Goddard and university scientists counted, using artificial intelligence and the planet data and other commercial satellite data, they were able to discover a large number of previously uncounted trees in the African Sahel. And they had a Nature paper about that. And then NASA satellites pioneered the use of ocean color remote sensing to see where there is, where the marine ecosystem is and its changes. And now, using the benefit of that synoptic view, combined with ships and in situ sensors to get at the vertical distribution of features in the ocean. We're undertaking to understand the role of the marine ecosystem in the ocean's carbon pump. So whether the ocean's acting as a source or a sink, and whether the biology that sinks out of the surface ocean, how quickly, how deep it's sinking, and this is part of the exports field campaign. That's a multi-year, multi-mission. So for sea level rise, this is altimetry that's been collected since the early 1990s. And this record shows us that sea level has been rising both due to the melting cryosphere and thermal expansion of the ocean. And all combined, the average over the past 30 years is approximately 3 millimeters per year of sea level rise, in some places more than others. And this map shows the spatial distribution of that. Next. And then we have active tools, near real-time tools to monitor fires with the Forest Service, both in the US and Canada. And we also have a lot of research ongoing to look at pre and post-fire vegetation, fuel availability, and whatnot. Next. And then this leads to forecasting global air quality. Our modeling, GMAO is our Global Modeling and Assimilation Group. They put out these forecasts of global air quality. This one is showing ozone. And so at ground level, that's a pollutant. And then in the stratosphere, it protects us from UV radiation from the sun. Next. And then NDVI, the Normalized Vegetation Difference Index, informs global agricultural outlook. So we've been in partnership with the USDA Foreign Agricultural Service for many years to help with global crop monitoring. And this helps to prepare for, there's also efforts with USAID on famine early warning system. So using NASA satellite data, they can anticipate where there's going to be humanitarian crises and plan food aid. Next. And then soil moisture is a newer, more recent input into our products with USDA. So working with the National Agricultural Statistics Service, this is a downscaled product to 1 kilometer. So using the in situ measurements to downsample the resolution of the satellite, this is an extremely useful product. Here it shows the areas that are green and blue have higher soil moisture, and then areas that are red obviously have lower soil moisture. And so this is very beneficial for, again, understanding the soil moisture in the land can gives information about drought. Next. And then altimetry can show us the heights of major lakes and reservoirs around the world for agricultural and regional security. Also, this is for Foreign Ag Service. Next. And our projection group at NASA GISS, they do the agriculture model in a comparison project, and this is helping to inform some of these smallholder farms that Stewart talked about in countries like India, Nepal, and Pakistan, where they're dependent on the hydrological cycle. The long-term projections from AgMIP can help with risk planning and helping them to make better choices about what to plant, for example. Next. Our models are also used for understanding renewable energy, for example, for solar radiation, solar panel placement, or efficiency and wind. Next. And then here's a specific example of working directly with stakeholders and having an impact on policy. In 2020, our colleagues at NASA GISS working with New York City, they passed heat equity legislation using NASA analysis of hotspots, so they can see where there are urban heat islands, and they were able to, in fact, you can see the nice blue rectangle in there is a cool area for Central Park, but they use that to pass heat equity legislation. Next. Okay, and then finally, this is my project. So I work with partners in the Chesapeake Bay to monitor water quality. Specifically, I work very closely with NOAA, who has operational jurisdiction over the water quality products in the Bay, but we're preparing for our upcoming hyperspectral missions. And we're working with Maryland Department of the Environment and the Shellfish Monitoring Division. There's a growing aquaculture industry in the Chesapeake at the same time that we've got more runoff from land during these extreme rainfall events. And we've got aging septic systems around much of the Bay. And we recently did have a runoff event that led to fecal coliform poisoning because there was a shellfish farmer who didn't hear that there was this problem with the runoff. So this is a serious concern, and we're hoping that by using satellite data, we can, and by using hyperspectral data, we can move beyond just looking at chlorophyll and water clarity, but start to detect some of these other features in the water and proxies for them. Next. And so this is getting ready for some of our upcoming hyperspectral missions, one of which is surface biology and geology. And the other missions that are coming are clouds, convection, precipitation, and aerosols, mass change, and surface deformation change. These missions are coming in the next 10 years. And next, this is going to be all together up on the cloud, having an open science framework. There was a press release about this last summer, and the goal is to better inform decision makers how our planet is changing on previously unimaginable scales. So we're just starting to get up onto the cloud and do open science. There's challenges. NASA lawyers haven't caught up to this. They're not letting us put our code on the cloud as easily as we would like, but it's a work in progress. So with that, I will end my talk and take any questions. Thank you.
Great, thank you, Stephanie. That's a lot of interesting work that's evolved in Earth Science Enterprise over the last 10, 20 years. I guess one of my questions is around NASA. Clearly NASA, ESA, JAXA, and the other space agencies of the globe have so many satellite programs and instruments, but still the oceans are terribly undersampled for a myriad of factors, but perhaps most importantly, dissolved carbon, right? And the science community has long assumed that the oceans are a sink for carbon. A recent study in 2019 showed, in fact, the Southern Ocean is a source of carbon for a significant portion of the year. Currently, there's a mission that is funded by Google.org, but conducted by your alma mater at the University of Rhode Island and European Commission on Medium Range Weather Forecasting and Saildrone, to evaluate the functions of the Gulf Stream, one of the great boundary currents, as it relates to being a source or a sink for carbon. If this basic assumption is wrong, what do we need to do to build a more accurate global carbon budget and model?
So getting back to Stuart's point about the importance of ground truthing and training data, and I'll mention, I believe the research you're talking about is by Professor Jamie Palter at URI,
right,
which did have National Science Foundation funding. So I'll put in a little plug for the federal government there, that is so important for our our science enterprise. But one of the great things that's happened over the past 20 years are these Argo Floats. So Argo Floats are profiling floats. They're autonomous. They're the last I heard, there were maybe more than 6,000. I haven't kept up, but those are really filling in our understanding of what's happening down to hundreds of meters in the ocean. And now they have probes with biogeochemical sensors on them called BioGeo Argo Floats. And those are really critical for filling in the missing gaps in our understanding of the ocean.
That's great, thank you. We have a question online. How do researchers connect to these data sets programmatically? What would be my first stop to incorporating this climate?
Yeah, so all of our data sets are publicly accessible. The climate data a lot of them are online. And for example, we have like the FuseNet and the hydrological modeling, the LDAS and the FLDAS and the GLDAS. Those are on, publicly accessible. Some of the models, some of what we're talking to potential partners about is having them actually run the models for their, downscaling it to their particular area. That's something that we currently do on our supercomputers. So we get people access to our supercomputers when they need to do that. That's one of the things we're exploring, the possibility of putting that on the cloud. It's a lot of compute to run those models, and so it's not trivial, but we're exploring that.
Okay, great, thank you. And I'm sure we'll have many more questions in the roundtable discussion. Thank you, Stephanie. All right, let's move on to Dr. Stephen Hamburg. Stephen received his undergraduate degree from Vassar College and his MFS and PhD from Yale University in ecosystem ecology. He was a postdoctoral fellow at Stanford University and a Bullard Fellow at Harvard University. Prior to joining EDF, he spent 25 years on the faculty of Brown University and the University of Kansas, where he served in numerous administrative positions in addition to his teaching and his research. He has served as lead author for the IPCC and was recognized as one of the scientists contributing to the award of the 2007 Nobel Peace Prize. He's also been awarded the US EPA Agency Merit Award, Region 1 twice, and he's published more than 100 scholarly articles and papers on biogeochemistry, climate change impacts on forest, carbon accounting, and methane missions. Welcome, Stephen. I can't wait to hear more about MethaneSAT.
Thanks so much. It's great to be with everyone, and it's really great to follow the last two speakers. I'll note that the first three letters of all of our first names are the same. It's a first for me. And I really would like to, if I get the first slide, really build on what was said before. So I want to talk, as Stewart talked about, the impacts on small landholders across the globe. Really provides the why for my my talk. Why am I going to look at methane emissions using remote sensing? And then Stephanie really talked about remote sensing in a broad strokes, and I want to sort of take all of that and to give you a specific example how we can take advantage of the sensing revolution and really make some things happen at a scale and at a level of impact that we probably never could have thought of before. Next slide, please. So as we think about methane, and we generally don't recognize the important role it can play within reducing the rate of warming over the next few decades, and thus the impacts that Stewart so eloquently described. So when we talk about methane emissions, I'm only talking about anthropogenic emissions. There are natural emissions that have been around for millions of years, if not billions. And we can think about those sources through this waterfall diagram. I'm not going to get into all the details, but we can think about agriculture, livestock, rice, fossil fuel production, and then waste, both from solid waste and landfills and wastewater. I'm going to focus on oil and gas today, but we really need to address emissions across all of these sources. And the good news is we really have momentum now. At the Conference of the Parties in Glasgow, we had for the first time a coming together of more than 100 companies to recognize the importance of methane as a greenhouse gas, and in particular recognizing how critical it is to reducing the rate of warming and thus the damages and impacts that Stewart so eloquently talked about. Next slide, please. And as we think about that, this is just some modeling that the team that I work with at EDF has done to really look at what are the real temperature impacts of these kinds of different methane mitigation opportunities. And so the top line is the business as usual, what we anticipate the climate impacts of methane will be moving forward. The yellow line is what we can do right now with basically minimal economic impact, and then what's technologically feasible is the green line, and then of course if we could fully mitigate all anthropogenic emissions is the bottom line. But you'll see, for those of you familiar with climate change, these are fairly big numbers. They may look small, they're tenths, from 1/10 of a degree Celsius to 0.5 degree Celsius, and if you eliminate them totally to 0.5 degree Celsius to 1 degree Celsius, those are huge numbers in the climate change world. And then below you see the different sources of that mitigation, oil and gas being the largest, chunk of it, but they across the different sectors. So we have an enormously powerful lever that we need to push down on to reduce the rate of warming. And we can do it quickly. If we can do it quickly, we're going to reduce the rate of warming quite significantly from an impact standpoint, both from human society and natural systems in the next few decades. Next slide, please. And just from the fossil fuel side, as I said, I'm going to focus on that as just illustrative because it is the easiest sector, the biggest sector where we can have the most impact in the immediate near term. So if we just model, so some people would say, well, we shouldn't worry about it because we're going to get rid of fossil fuels. We need to address climate change, and we absolutely do. But timing matters. So the graph on the left-hand side shows what the trajectory of emissions would be from the oil and gas sector with no action. What would they look like with a decarbonization only structure in the time frame? It's a little faint there. Goes out through 2050. You could argue that that's not as aggressive. These are data from the International Energy Agency. But the key here is that we need to decarbonize and reduce methane emissions from the fossil fuel sector at the same time, because when we do it really matters for the temperature impacts over the next couple of decades, because methane is the dominant determinant of the emission of the climate warming we're going to experience over the next couple of decades, more so than CO2 from the emissions over that period of time. So methane is really critically important to the damages that I'm going to experience in my lifetime. And we can reduce oil and gas methane emissions by 70%, according to the IEA, and we can roughly half of them will pay for themselves. So literally in the net, they're free, and we can do much of it at really limited costs. Next slide, please. So what do we need to do to address greenhouse gases to meet the climate crisis? We need to know what's being emitted, where it's being emitted, how much is being emitted, and how are those emissions changing over time. And this is the role for the International Methane Emissions Observatory. I'll come back to that. But this is the challenge we have across greenhouse gases across the globe. Currently, we do not have a mechanism by which we actually collect empirical data to answer these questions and present that openly to the world. We're beginning to see a revolution using both remote sensing and integrated systems that Stephanie talked about to be able to bring this data to the world, open for everybody to look at. And we believe at EDF, and I believe personally, that this revolution will change the rate at which we can start to ameliorate the emissions and thus the impacts. Next slide, please. This is just an illustration of some data from Alberta, Canada. Just, the kind of problems we have with data quality with respect to greenhouse gas emissions. On the right-hand side, you'll see from Alberta, on the left bar, the green one is what the industry reported emissions are. The official inventory is a bit higher, but not a lot higher. And then directly measured data is multiples of that. This is not ubiquitous, this pattern, but it is the norm. Most cases, the reported emissions are less than the actual emissions. So the key is, how do we create accurate data that characterizes emissions across sources and across the globe? So I've been working for the last decade with a host of hundreds of scientists from around the world to begin to build this picture of what is being emitted and how much is being emitted and how it's changing. Next slide, please. So these are data from a synthesis that we published in Science a few years ago, taking all the data we generated over the preceding 7 years. Again, a couple hundred scientists across at least 50 different institutions. And you'll notice on the blue bar, and this is going across the natural gas supply chain from drilling and production to gathering being bringing all the gas together, processing it to produce a uniform product, transmission and storage, making sure it's available to you. And my house here sitting in Providence, Rhode Island, I have a natural gas boiler in the basement that I can turn it on and off as it's It's cold, it's been cold recently and it will get cold again. And then of course the local distribution to get it into my house. And we see, of course, the drilling and production is where most of the emissions occur, but the emissions are basically double what the EPA suggested. And since we published this paper, actually the estimates for EPA have gone down. Emissions have actually empirically shown to go up. So there's a major gap between what we say the estimate is and what the empirical data is. Now, this took lots of people working, lots of scientists, pulling together all the data to create this global, this US national estimate, which had never been produced with empirical data before. But we need to be able to do this basically on a routine basis. So if we can think about this as a snapshot of what's going on, we need a motion picture. We need to get this continuously. We need to know how it's changing and how it varies spatially. Next slide, please. So to do the work that I described here, we have top-down methods from aircraft on the left, on the top left, and a tower, a tall tower on the right, top right. And we can use these approaches by measuring the methane and using different types of transport models to inversions. We can calculate what the mass of methane's being emitted from a region or an area. We also do it from bottom up. We go out in the field. You see the picture on the left with some researchers working at the University of Texas, study we did a few years ago, looking at individual sources and quantifying them, or a project we did jointly with Google, where we used a street view car with instruments in the rear, and we were quantifying methane emissions from local distribution leaks over tens of thousands of kilometers across 13 cities in the US. So we can do these methods, we can do it in site-based, making sure we have accurate estimates, but again, we need to scale this. And this was a point that was made. We really need to scale the data. We have to have lots of data. We need to be able to do it in an integrated way. Next slide, please. So that's where we come to using a satellite technology. I'm showing you my favorite satellite because I'm co-directing the construction of MethaneSAT. This is a philanthropically funded satellite, and I'll talk about it more later. But we really need, as I said, to have this motion picture, collecting data regularly, being able to process it. But we have to do it in a way, as I said, that produces what's being emitted, where it's being emitted, how much is being emitted, and how it's changing over time. The satellites now flying to measure greenhouse gases don't do that. And part of that is you get concentration data, but it doesn't take it all the way to policy relevance. The key is building that entire ecosystem, automating it. And in the case of MethaneSAT, as Stephanie talked about, everything's going to be done in the cloud. We're already in the cloud. We're already building the algorithms, testing them with aircraft-borne measurements. So it's a cloud-based system to provide global data on oil and gas methane emissions with a greatly increased level of precision. Next slide, please. And what we can do with these kinds of data using existing satellites, this is from Tripomi, which is a Sentinel-5P based instrument. This is the European Space Agency. Once the satellite went up, we started using the data, took 11 months, and quantifying methane emissions, in this case for the Permian Basin, which is in the US, the largest oil and gas producing region in the country and one of the largest in the world. Now, this gives you concentration data. But again, that's not policy relevant. We need to know how much is being emitted, where it's coming from. So next slide, please. We can then use an inversion process to be able to generate on the right-hand side the actual emissions and quantify them to the total emissions, which, as you'll see relative to the prior, which is the inventory, is more than 2 times higher. And now the challenge we have with Tripomi is you'll see the pixel sizes are quite large. So we can't really get to a policy relevant, who should do what, we don't know. We know what the total is. We know how it varies over space in a general way, but we don't have the level of granularity that we need to really make the data actionable so we can reduce emissions effectively and assign those emissions to specific facilities. Next slide, please. So these data are just showing you the different types of satellites. At the top, MethaneSAT, which will go into operation in 2023. It's got a grid size of roughly 1 by 1 kilometer with actually subpixel, the native pixels of 100 meters by 400 meters, with swath of 200 kilometers. and a precision of 2 to 3 parts per billion. Now, this is important because we want to be able to characterize all emissions from fossil fuel production, particularly oil and gas, and we want to be able to ensure that we can do it around the globe and see all of the emissions that are occurring. Now, there are other satellites. No one single satellite is going to be able to provide all the data. We have some of them already flying. I mentioned Tropomi in the middle of the list, which is the European Space Agency. We also have GHGSat, which is a target mode instrument. So you're seeing small areas. Tropomi, very broad swaths, a higher precision. So it helps give us a background, as I showed you for the Permian, but it doesn't give us the data that we need to fully go to have the data necessary for implementation. Next slide, please. So what I'd like to do is I'm going to show you a video of comparing and contrasting 3 different satellites and their complementarity. So the first is Tropomi that I talked about, sort of giving these global mapping of what's going on. And then we're going to see GHGSat, a target mode that takes subspots, they direct it, and then followed by MethaneSAT, which is going to do large areas with high degree of precision where we can see and quantify all the emissions and make heat maps, totally understanding where the emissions are coming from. So this is a contrast of the kind of remote sensing data. And what we're doing is fully automating the inversion process so that the data that we generate is what's called level 4, which is flux data that will give us exactly what you see here, will give us a heat map at a very fine scale so we can do source attribution. We'll see large point sources, and we'll see the total emissions from these large geographies around the globe. Now we'll have, for the first time of any greenhouse gas, detailed quantitative data in near real time, and having with repeat measures from year in and year out, where we can start to understand the patterns of emissions, who's responsible, and what actions are being taken, and how effectively are they mitigating emissions. Next slide, please. So if we could hit it again so we move on. Thanks. So the Methane Mission, as I described, the primary goal in the near term is to help catalyze a 45% reduction in methane emissions from the oil and gas production by 2025. And as I mentioned, this is fully funded philanthropically, putting together a team who is building it from commercial space and academia and people who've worked in government, and bringing everyone together to do this. We're going to do it for all the oil and gas production regions, and minimum of 80%. We're going to get area emissions and point source emissions, and it's going to all be with a flux data product that really allows us to be policy relevant from day one. All the data is publicly available. It'll all be, and the scientists can get into the details, and the rest of the world can see it. Next slide, please. And then, but that's an integral piece of it, but it's not sufficient. I described different sources of data. So announced just a little in 2021 is an effort called the International Methane Emissions Observatory, where we want to bring all these data together, all the remote sensing data, the science data, data from the companies voluntarily reporting their data, as well as the inventories. And this is under the UN Environment Program. We're going to have the science, it'll be transparent, and allow for implementation, providing solid data integrated on a global basis by an important global multilateral that is trusted. Next slide, please. And to do that, we've got to do, as we described, we've got to use a whole host of machine learning and AI techniques. We got to reconcile the data across these different platforms. We've got to then generate final products that people have confidence in with transparency, so that then decisions can get made in the political arena and at the country level and globally and even at the local level to affect strong mitigation options, and in turn reduce emissions and address the climate crisis at a scale and at a pace that up till now we've not been able to do. That's the vision. We very much hope we can realize it. IMEO is off to a strong start. As I put on the beginning, I chair the Science Oversight Committee that's about realizing this vision on the data side. And last slide, and thank you very much.
Great. Thank you, Stephen. That's fascinating. I've watched the formation of MethaneSAT LLC for years, and the weaving of your suppliers from your partnership with New Zealand and SpaceX and Blue Canyon Technologies and Rocket Labs. You certainly have threaded that geopolitical science needle. Well done. I'm interested in your business model. So you talked about the data being open for the science community. I assume you've got to generate some revenue. Is the idea that you will service commercial consumers and government regulators on a fee-for-service approach, or
all the data is the L4, L5, L4 data. So everybody free of charge, no matter who you are and where in the world, will get that product free of charge. If you want to, everyone will have to sign a license agreement which says you will not commercialize it. That's the only restriction. If you want to commercialize it, then you have to get in an agreement with us. But we have funded this philanthropically. And so the only costs that we have are operating. And as you said, we have a partnership, which I failed to mention. Thank you for raising it, with the New Zealand government. And we are exploring what the income might be from that commercialization. But the overwhelming majority of our costs are done philanthropically. And we in no way are going to restrict access to the data. We believe transparency is the most effective tool for affecting rapid mitigation, which is what we all need to address the climate crisis.
Right, okay. So in your data streams, if there are methane emissions detected at coal mines or natural gas facilities, what process is MethaneSAT and EDF going to use to ground truth these anomalies? How is that going, or not anomalies, but signatures?
It's observation.
Yeah. How's that going to work?
So of course, the remote sensing itself is with the TCONs to just make sure we're getting accurate data from the sensor, the spectrometers. But we also, because we're doing ground-based work, the science that I described, we're having a lot of validating data collected on the ground to ensure that, in fact, we're getting an accurate picture. We've already started that work. We've put the instruments on a plane and flown it. We have actually undertaken a controlled release experiment this past summer. Those results are just getting worked up. We also are comparing it across different instruments. So you can also use instrument spectrometers that look up, and we'll be doing that while we let the instrument looks down. So we have a whole large validation and calibration program. So, and we will have, of course, we will report our uncertainties. So it's not going to be, there's not zero uncertainty, but we'll make sure we're going to minimize it. Now, part of that is taking repeat looks so that you can reduce the uncertainty. So we'll provide that. But we believe because we designed the instrument explicitly to have maximum precision. So that's, as you saw on the chart, we have anticipate having better precision than any of the instruments flying and planned right now. That will allow us to reduce the uncertainty while keeping the spatial resolution policy relevant, while still having a wide enough swath to capture entire oil and gas basins.
Oh, that's great. So I'm also fascinated by the function of the International Methane Mission Observatory. It sounds like foundationally very important to global science. Is there a similar repository planned or in the works for a collaborative process for other GHG gases or science measurements?
I'm not aware of it. Now, science measurements are brought together. This is key of trying to bring all of it from the industry and everything together. I'm not aware of it, though I'm a big proponent. I think this is exactly the model we need across all the greenhouse gases, with total transparency, third party, everything brought together and integrated. And there will be challenges we'll have on that integration because no one's ever tried that. There will be inconsistencies. We'll be honest about them. We'll say, here's a place where there's differences and we can't explain it. Now, a lot of the times, what we're seeing is I like to use the metaphor of the elephant. So one person's looking at the rear end of the elephant, another one at the front end, and then it looks like they're different, but you just have to recognize you're seeing the same elephant from different angles. So a lot of the data that we collect is actually consistent, but it's hard to recognize that they're actually looking at the problem or the observations in different ways. That's the kind of work at IMEA will do to make sure that's clear to people that these are, but where they aren't consistent, you know, when the elephant it looks two different sizes, depending on the data, we'll just say that. We believe we'll be able to resolve most of those, and we're doing some initial work using different methodologies, including remote sensing now in some of the basins where there's ongoing work, so we can see to what degree that and what are the issues we need to do to reconcile across measurement platforms.
Right. Okay. Thank you. Thank you. That was fascinating.
Thank you.
All right. So we have 20 minutes left, and I want to pull all the panelists back together and put out a few questions. I know we've had a constant stream of questions from the audience as well. So I want to take about 10 minutes to go through the panel discussion, and then we'll roll through a few more of the audience questions. So welcome everybody back. So finally, the issue of climate change, mitigation, adaptation, resiliency, they're all getting the attention and funding that the science community has been screaming about for years. However, our community had a history and reputation of doing lots of projects, but very few consistent long-term programs designed to supply information to regulators, policymakers, businesses, and actors on the ground. How do we ensure that the money allocated in the infrastructure bill, and if it comes to fruition, the Build Back Better, makes a difference in our environment and our ability to mitigate and adapt to climate change? How do we work together as a community to create workflows that are directly consumable and actually support climate mitigation and resiliency? I'll just open the floor. Who wants to jump on that first? Nobody?
Well, I'll jump in. I think the key is ensuring that we demand, we the science community and then civil society writ large, both in the US and the global, that the data products that we produce are what I like to call policy relevant. They have to be good science. And I think, Stewart, you spoke to that very eloquently. And as did Stephanie, what do people need to make decisions that can either reduce their contribution to or adapt to the climate change that we're experiencing? And we haven't done that. We haven't demanded that. And I think there's no reason why we can't. And Stephanie spoke to how NASA is beginning to pivot to do that. Well, we need to demand faster pivoting from everybody, including the NGO, all sectors, the commercial space, government, NGOs, et cetera. But I think we're starting to see it, and we just have to make that demand. You can do good science, you can advance science at the same time as you're producing products that are relevant to dealing with the crisis that we're in.
Yeah, and then I think the key for NASA and other government agencies will be clearly understanding, first of all, partnerships are essential. We really need to work with others who have the mandate, you know, with operational agencies or NGOs or private sector. And then getting a really clear sense of what is it that government can do and where does government's role end and private sector pick it up.
And maybe just building on the point Stephen made and Stephanie, and this is in the context of low and middle income countries, not necessarily domestic issues here in the US, but one approach we found quite successful is, even though my work is focused on small scale producers, so farmer facing solutions and climate adaptation for those farmers, yet we really need to work closely with government because they have the mandate, they have the ability to set policy. And one technique we've used that's been quite successful is providing them visibility to this data. So, as Stephen said, the right types of tools and products that are consumable and give visibility to the issues. So whether that be water management or changing agroecological zones, presenting that information to policymakers, regulators in an easy to use way is really important to get their buy-in and to leverage that mandate that they have, and ultimately leads to more action, more opportunities to invest in reaching small scale producers in my case.
And I would just add towards that point, which is Stuart's point, which is an excellent one. We work with social scientists. So it's not myself, a scientist, who decides what's the form of the data, working with social scientists, trying to make sure that our data that we generate is actually consumable and addresses the needs of multiple constituencies. So there'll be a variety of, the data will be in multiple forms to ensure it's addressing the needs. The other thing I just wanted to say to Stephanie's point is MethaneSAT is an unusual collaboration. We need more of those, right? We're an NGO that took on the task of building a cutting edge satellite, but in collaboration with others, governments, et cetera. We need to start thinking outside, coloring outside the lines and recognizing, and I think Stewart and the Gates Foundation is a great example. We need to start to think about, we need new collaborations and new models of getting the data that we need to address this issue. If we do it the same old way, it's going to take too long.
Another question for all of you. What are the barriers to deploying technologies like machine learning and AI for remotely sensed data in each of your respective work streams?
Training data and labeled data is a huge challenge. So for example, for water quality, we're trying to take advantage of the synoptic scale that we get from satellites, but we really need ground truth data to verify what we're seeing, and to fill in when we have clouds or something else. And so collecting data is going to be essential for training machine learning. And then the other issues with satellite data are, cloud cover and other things that interfere with having a complete picture.
Yeah, and that's the the work we're doing on the enabling crop analytics at scale. Is we're hoping to try to address that issue. In addition to that, I'd say a lot of our partners lack technical capabilities to consume that data or leverage the latest tools. It's a very confusing space. There's a lot of techniques out there that are not all that well known, and how do you match that to specific use cases? If you're trying to predict a pest or disease outbreak, or if you're trying to build an application that provides very specific advice to small scale producers. We're often working in low and middle income countries with NGOs and governments who don't have the Silicon Valley level technical expertise. So trying to address that TA assistance component or capacity, I would just say also trust in these systems and transparency as to how they operate and how the results come out the other end of a black box. And then finally, policies that enable these solutions to be used at scale. We've certainly encountered some overreactions in terms of policy regulation on use of data in some countries we work in that can mitigate the use of these tools.
I agree very much with what was said, and we're certainly doing some of that same work. And I would just add one point, which at least from a mitigation, is to ensure that all the data layers you need to understand these issues are totally transparent, because that's not currently the case. So for example, in the oil and gas sector, but in pretty much across most of the methane emission sources, we don't have global databases, comprehensive global databases of what's being emitted, what could potentially emit things. So we're actually building a global oil and gas database that will be fully available globally. Right now, you have to pay. It's behind paywalls, which means most people don't have access to those data. But certainly, I absolutely agree on training data and ensuring that that we have the skill sets across different communities is integral to succeeding.
Yeah, absolutely. And I think I was going to ask the panel a question about the importance of open data, right? In moving forward with the big task at hand. And I think not only does it need to be open, but it needs to follow the FAIR principles, right? That it is findable, that it's accessible, that it's interoperable, and that it's reusable. So, and many times you'll hear that the data is open, but you can never find it, right? So We have an interesting question that can start a long conversation from the audience for each of you. Do you have any concerns about the public's ability to digest this data objectively? Sometimes we don't deal well with uncertainty.
Well, I might take that on because, as I mentioned, we actually test that. So I have social psychologists on in my group, and we actually do the experiments for exactly that. We've already been doing them with air quality. We've done them with other methane, because that is a big issue, is how do we convey the data in a way that doesn't, we're not trying to dumb it down, but make sure it's accessible to different audiences, and testing that very explicitly through a series of experiments. So we bring the science to exactly that issue in the way we do in collecting the data. Is we have to bring science to how do we disseminate it so people are comfortable with it and are, you can't help someone, I mean, anyone can use data improperly, but at least giving them the tools to be able to understand the data and ensure that it has a high likelihood of being used that way. And I like to say in some of our early projects a while ago that my instincts as a natural scientist were completely all wrong in how we should present the data. And I was very glad to have a professional social scientists who know how to do this work to correct me and make sure the data went out in a way that was accessible. And we had very good luck with that. We had a lot of people concerned that as we put data out that people would think they're crises and problems and call 911s and all that kind of stuff. And it didn't materialize.
Yeah, I always think of the ensemble models where you sort of see multiple sources for similar models or different approaches, where you can very easily consume those types of charts and sort of essentially making your own decision on what the range of risk is. It's certainly an area we think a lot about at the small scale producer level, because the most trusted source, even though farmers never see an extension agent, it's still their most trusted source of information. And so how do you build in the messenger into these information delivery tools? You're not circumventing people by directly going to farmers with information on a phone. You're thinking about how do you build in this information to their normal information workflows. So who is the trusted source? You provide them maybe richer information that they can then explain the nuances of some of that data to their audience that they already work with and have a relationship with. So challenging problem for sure in this day and age.
So we have another question from the audience, but I think it's really should be addressed by all three of you. And it says, will we ever be able to build, will a farmer be able to get credit for having sequestered carbon? I guess the question also is, can we peg a value to carbon? Is all carbon sequestration created equally? And with the carbon markets starting to evolve, how are we going to deal with that?
I am probably the least qualified to answer that here, but I'll try. I mean, it's still very early for us. I mean, we're watching what's happening with some of these carbon offset payments, through groups like Indigo and others are starting to assess a price, and this is for commercial high-income country markets. There's some experimentation in smallholder farmer environments, but I think the challenge is our experts on the call here around measurement, consistent measurement and quantification and agreement on what that is. So, what is a practice and what does that equate to in terms of value? I think still a lot of work to be done there.
I would agree with Stewart, though. I think that we can look to avoided deforestation, the work of Emergent, where I think you're seeing some real progress and some announcements at COP relative to collective action. And the key is one of scale. If you do it at a larger scale, you can deal with the measurement, reporting and verification issues much more easily, because you don't have to deal with the leakage, basically something happening in another place, or the additionality that your actions wouldn't happen without the intervention for which you're paying. The challenge is, of course, you need to keep your transaction costs low, particularly if we're talking about the kinds of small landholder farmers that Stuart's talking about. And to do that, you scale it. Early in my career, I've spent a lot of time, actually many decades, measuring changes in soil carbon. That's my own area of expertise. Nobody could afford for me to do it for their one farm. Certainly, if you're a small farmer, a small scale farmer, I've done work in India on that with small landholders. You can't afford that, right? It will cost more than the carbon could ever possibly be worth. But you can do it when you aggregate across areas where you're really caring about accuracy and less about precision. I mean, I'm getting a little bit in the weeds here, but those are the kinds of issues. And we believe some work that we do, we have a large team working on it, that we can crack these problems and figure out what the realistic potential is for using natural climate solutions to address climate in a way that has high integrity. It's going to be realistic. It's not going to meet the maximum potential that some people talk about, but we can tap it and we can use remote sensing. And again, I think the best example is in the avoided deforestation. Remote sensing plays an integral role, and it has high integrity if you do it at jurisdictional level.
Right. Stephanie, a question for you from the audience. With the advancements in remote sensing for applications to water quality and monitoring, what do you see as the biggest research gap or need that's just yet to be adequately addressed?
Yeah, so that's really interesting. You know, we're hoping that hyperspectral remote sensing will add a lot of nuance to what we currently see with multispectral. So we're doing a lot of data collection, field data collection, and then lab work to understand, you know, for example, the species composition. So what are the communities and are they changing? And then their role in the carbon cycle. So I would say that the biggest gaps are having enough, in situ measurements to really know what we're seeing with all that spectral information. That's the thing we're working on the most right now.
Training data again, right?
Yeah.
Yeah.
Training data for machine learning, and also for building just regular geophysical algorithms. So,
right.
I think that's going to be really important too.
Okay. Well, I think we have time for one more question, Stephen. It's for you. It's a big, hairy, audacious policy question. We know that China is emitting large quantities of methane from its coal mining facilities. Will there be a concerted effort to determine if coal-related GHG emissions, which are reported by the National Inventory to the UNFCCC, are accurate? What about all countries such as Turkey, Australia, Poland, the US, etc.?
Absolutely. So IMEO's working. We started with oil and gas in IMEO simply because the science was further along, but there's an explicit commitment to work on coal mine methane. We have some projects that are teeing up, and remote sensing and even some of these target mode instruments are really well adapted to that, because these are large point sources if they're deep mines with vents and things like that. You don't have to survey large areas. You can know where they are. So absolutely, and I wouldn't pick out China, though they're the largest coal producer in the world by far. But there's already data. There's some recent data from remote sensing in Australia, coal mine methane emissions being very high. You bet. We need that data. We need it globally, and there's a commitment within the UN Environment Program, which through IMEO, to collect that data, do high quality, and present that globally. That's how we're going to move things forward. So we have a transparency. My job isn't to make the policy decisions to what to do about it. I have personal opinions, but my job is to try and help integrate that data so people who do have the responsibilities will make well-informed decisions. And I do believe that with that transparency, we will get a better outcome.
All right. Well, perfect. Thank you. Thank you, panelists. I think we are right on time. I really enjoyed this conversation. I hope those in the audience have as well. And I'm going to turn it back over to Doug. Doug?
Thank you, Anne. And again, to our esteemed panelists for a wonderful and I think a very important conversation. And thank you for all of our attendees who have joined us, and certainly for those who engaged with questions. You will all receive a follow-up survey, and we welcome your feedback. And if you want to engage further, either labs@mitre.org or policy@mitre.org are great ways to do that. A reminder, MITRE is hiring. So if you're interested in tackling any of the challenges that we've talked about today or others that MITRE is engaged in, please don't hesitate to reach out to recruiting help at mitre.org for more information or hit our website. And last, but certainly not least, we're excited to announce a special edition of our Grand Challenges Power Hour in just 2 weeks on January 28th. And it's timed to coincide with National Data Privacy Day. We're thrilled to have Senator Ed Markey joining us to talk about the National Data Privacy Law and some of the unique engineering opportunities and challenges that would be involved in implementing such an effort. So registration for that is now open, and we're copying a link into the chat now so you can register for that. So with that, thanks again for joining us, and I hope everybody has a great evening.